So in my last video, I talked about two things that regulates hemoglobin, and that was the pH and the concentration of carbon dioxide. And I inferred, or I said at the end of that video, that there's another regulator, and that is this one, 2,3-bisphosphoglycerate, or we just abbreviate it. Is there an abbreviation on the slide? No. Let's put the abbreviation that we are going to use for this guy. BPG, okay? Bisphosphoglycerate. This molecule is bound to hemoglobin. When you take hemoglobin out and you look at it, there's a lot of this BPG present. Or better yet, better way of saying it, in our bloodstream, there's a lot of BPG, okay? And this BPG is a negative regulator, and clearly it's a heterotropic because what binds to hemoglobin? Oxygen. Okay, and we know that oxygen, when it binds, it promotes binding of the next site. So it's allosteric, right? It's undergoing allosteric regulation. So we have the oxygen, first binding site promotes the second, third, and fourth, right? But now we have the heterotropic regulator, which is BPG, and we see that that is going to, when that binds to hemoglobin, it's going to limit the ability of hemoglobin to bind oxygen. Or look at another way, it's promoting the release of oxygen. And I said it's very concentrated, millimolar concentration. Okay? And that's in our erythrocytes or red blood cells right there. So another very big key point right here, I said when BPG binds, it reduces the binding affinity of hemoglobin to oxygen. And so if that's true, then we've learned up to this point that the T state is the conformation of hemoglobin that promotes the release of oxygen, or low affinity. So that's exactly what BPG does, is when it binds to hemoglobin, it's going to stabilize the T state in such a way as so it can release the oxygen. Now, what I want you guys to know is that BPG, it's only one molecule for hemoglobin. And there's this cavity right in the center of hemoglobin where BPG goes in and binds. And when it binds there, it stabilizes the T state. Okay? But when that is released, you can see that hole shrinks. Okay? And when that hole shrinks, then it's stabilizing the R state. So what I want to talk about next is why this is so cool. There's a couple things that we're going to do about or talk about about this molecule that makes it really cool to me and very, very interesting. So let's set the stage for this graphic here. So you see that there's three curves. We have a black one, a blue one, and a green one. The black one we're not going to focus on at all, other than that's hemoglobin where we've ripped out the BPG. Okay, so it has a 0 concentration of BPG. What we will focus on is the difference between the green and the blue curve. And the difference is the blue curve has 5 millimolar of BPG, and then the green one is 8 millimolar. And why is there a difference in concentration? That is because the blue curve is at sea level and the green is in a higher altitude. So let's say the mountains. Now, this is interesting in the fact that depending on the altitude that you're living at, your concentration of BPG is going to change. And this is the spoiler alert. Why do you need different amounts of BPG at different altitudes? And the reason is because at different altitudes, your hemoglobin it needs to be able to release the same amount of oxygen. Your tissues need X amount of oxygen, all right? And so if you're at low altitude versus high altitude, that output of oxygen that's being released to the tissues has to be relatively the same. But if we got rid of BPG altogether and you lived at different altitudes, the release of oxygen that your tissues would receive would be different. So if you're at sea level, and there's no BPG present, you would give off more oxygen to your tissues than if you were in a high altitude. At high altitude, you would give off less oxygen to your tissues. So you can see that that's a major problem, right? If you live in the mountains, you're not going to get enough oxygen to your extremities and the tissues all over your body. So BPG helps to make that the same. Doesn't matter what altitude you live at, you're going to get the same amount of oxygen released to the tissues. So that's the end game. That's the big reveal of what PPG does. Okay. So let's take a look at this curve here. Let's focus at this point right here. At that point on the curve, it doesn't matter if you're at 5 millimolar or 8 millimolar of PBG, because you see, look at that. Oxygen is going to bind to the hemoglobin no matter what. It does not matter what your concentration is. Doesn't matter what elevation you live at. Well, sorry, when we're at sea level. When we're at sea level, it doesn't matter what concentration your BPG is because the binding of oxygen is going to be the same at that point. So that's not where we want to focus our attention at, because remember, I just talked about how we want the release of oxygen in our tissues to be the same depending on your altitude. So what we really got to focus our attention on is the release of oxygen. Okay, so the release of oxygen in our tissues at that point right there. Okay, so let's clean this up a little bit here. Okay, so what I want to focus on is the blue curve. So the blue curve, if we extrapolate all over here, what is the Y value going to be? Approximately 0.06. So that means when the hemoglobin gets to the tissues, okay, it's 60% occupied, meaning the hemoglobin has about 60% of its sites full of oxygen. Okay? And so when we have the hemoglobin in the lungs at sea level, we have more or less 100% of the hemoglobin occupied with oxygen. So I've lost the word. It'll come to me later. But basically, the hemoglobin is that's the word, saturated with oxygen. So from this point on the blue curve, okay, to this point, right there in the lungs, how much oxygen has been released. It's 100% here, it's 60% here, so that is roughly 40%. And in this graphic, we're showing that it's 38%, okay? So the hemoglobin goes to the lungs, gets oxygen, and then goes to the tissues and dumps off 40%. So if we go to a higher altitude, we have to have the same output, or we're going to have trouble. So let's continue with the blue curve. What would happen if the concentration of BPG stays the same if you go from sea level to a mountain, and it stays at 5 millimolar? Look at what happens. So the partial pressure of oxygen in your lungs at a high altitude is right there. Okay, so clearly when you go extrapolate over here, it's not as saturated as it is over there. So there's less oxygen in the hemoglobin when it gets to the lungs. And then when that hemoglobin goes to the tissue, right here, it gets to that point right there, what's the dump off, or what's the unloading percentage? 30%. So if the BPG concentration stays the same from sea level to a mountain, you are losing what? Nearly 10%. Well, in this case, 8%. So your tissues are getting 8% less oxygen than they should. And that's bad. And so how does the body compensate for this? When you go from sea level to a higher altitude, the concentration of BPG in your blood changes. It increases. And why do we want it to increase? Because take a look. When we look at the green curve, which is our BPG and hemoglobin, you see here, at sea level, still saturated just the same, okay? But the point that we want to look at is this one right here. At higher altitude, we're going to get what? Less affinity of oxygen to hemoglobin. Okay? There's less oxygen there. But when we get to this point, right, this point right here on the green curve, right there, what's the dump off? What's the payload? And that's what you can't really see very well because there it is. You see that line right here? From that point all the way to that point, how much oxygen has been released? 37%. So 37% and 38% are very, very close. So that is why the BPG concentration has to go up. It lowers the affinity of oxygen to hemoglobin, which then in turn gives off more oxygen. Well, it doesn't give off more, it makes sure that percentage of the payload is the same. Isn't that so cool? And they've done experiments where you go from sea level to a higher altitude, and within like a day, there's a change in concentration of your BPG. It happens relatively fast. Another cool thing that I think you'd be interested in looking at is the hemoglobin in babies that are in the womb compared to the hemoglobin in the mother. Okay, so clearly a baby in the womb isn't using their lungs to get oxygen. So they have to get their oxygen from the mother's blood. And so babies have a slightly different looking hemoglobin that has a higher affinity for oxygen than the mother's blood or the mother's hemoglobin. And you can read more about that in the textbook, and there's a problem in the end of the chapter that I'd highly encourage you guys to look at because it's very informative, it's cool, and it's an application of everything that we've been learning here. So in my textbook, it's problem 8, and the problem says comparison of fetal versus maternal hemoglobin. And so it's going to teach you some cool things and then as you analyze it. So I think that's a good spot to stop for this video. Just double check here. And I will mention one more thing. I have some former students that are getting ready for the MCAT, and they're like, this problem right here shows up on the MCAT. And they like focus on this right here. So very important topic.